Okay, welcome everybody to the annual VTSS workshop. It's my pleasure to introduce Gabriele Mingoli, who will be talking to us about modeling common bubbles, a mixed causal, non-causal dynamic factor model. Gabriele, the floor is yours.
Perfect. So my name is Gabriele. I'm a PhD student from the Vrije University in Amsterdam, and today we will talk about common bubbles. So let's start with some definition. What is a bubble? So speculative bubbles can be defined as locally explosive episodes, as they are characterized by this explosive growth towards a sharp and sudden mean reverting pattern, and is often called a crash. Now, when these explosive episodes propagate simultaneously across different time series, they can become a crucial source of instability for the markets and the economy. And this is because many elements of the same economy are then exposed to the same extreme event. Here I have an example of a common bubbles in monthly stock prices from companies in the energy sector. And the darker areas in the plot show the co-movements in the series, and especially the sharp increase and the sharp crash that is experienced by most of the series in the sample around 2008-2009. Now, since common bubbles can have this disruptive impact on markets and economic agents, it is crucial to be able to identify and model this phenomenon. At the same time, existing models for common bubbles all suffer from some type of limitation. For example, some of them are limited only to the testing for the presence of a common bubble, like the approach from Chen, Phillips, and co-authors that focus on an explosive root testing to detect common bubbles. But while their approach is very interesting, they are not able to model these dynamics and, for example, forecast the evolution of the processes during a common explosive episode. Other approaches suffer from computational issues as the cross-sectional dimension n grows. So these other models, as soon as n becomes 5, 6, or 10, cannot be estimated and cannot be used to forecast. And importantly, most of them are limited to stationary setting. And this is a problem because many of the processes that actually experience explosive episodes are non-stationary, like stock prices or commodity prices. And in this sense, my paper tries to solve all these issues. And to solve these issues, the paper proposes the first model that is able to model common bubbles in a high-dimensional and non-stationary setting. How is this done in practice? This is done through a simple common factor model where an observed high-dimensional time series weight t is driven by a lower dimensional set of unobserved common factors ft through some loading matrix, and on a vector of unobserved idiosyncratic components bt. Now, this is nothing new. The contribution here is that these unobserved components, both common and idiosyncratic, can experience their explosive events and can be modeled in a non-stationary setting. So this is a bit the idea and the goal of the paper. So let me move a bit more in detail about the model. So the first question that we have to answer to build a model for common bubbles is, how do we model explosive behavior? This is done relying on mixed causal non-causal models, also known as MAR models. A MAR model allows a process to depend on its future through a lead polynomial, similarly to what a standard backward-looking autoregressive process does on the past with the lag polynomial. Now, importantly, in this literature, the term causal and non-causal stand for backward-looking and forward-looking. Here I have an example of a mixed causal non-causal model, the simplest one, the one where the process depends only on its future. So xt is equal to psi xt plus 1 plus epsilon t, where epsilon t is a sequence of heavy-tailed innovations. Now, the heavy-tailed assumption is actually a crucial assumption for MAR model because it's exactly the extreme values in the tails that jointly with this forward-looking dynamics create this explosive growth towards a sharp crash, a bit in a symmetric way with respect to a mean reverting pattern after a shock. And this is exactly the trajectory that we can see in the plot below, where I simulated from such a process imposing only one shock different from zero, we can see this explosive growth towards a crash. If we want to be more general, we can define a MAR RS, where a process depends on its R lags and S leads through respectively the causal and non-causal polynomials, phi and psi. Now, this can be easily extended to multivariate, similarly to VAR for autoregressive process. But if we want to make sure that the that the explosive dynamics described by this MAR model describes a common dynamic for an observed dimensional system, we can simply include the MAR dynamics into a more complex dynamic factor specification. So in this sense, we can assume that the observed process depends on an observed component that will be modeled through a mixed causal non-causal specification, as in the model that I present here, where YT depends on an observed components FT and VT, and FT is modeled as a multivariate MAR model, where psi z and phi z are respectively the non-causal and causal matrix polynomials. So FT will experience its explosive behavior, and the bubbles that will arise in this common unobserved component will then propagate through the system through the loading matrix, becoming the common bubbles that you observe in the data. Now, importantly, if we want also idiosyncratic explosive behavior, we can simply also model the idiosyncratic components through a MAR specification. Here, for example, I put a purely forward-looking model as a simple example of this type of modeling choice. So this is already something new in the literature, in the sense that I can estimate this model. It's a perfectly viable model to model common bubbles in a high-dimensional setting. But where is the non-stationarity? The non-stationarity can be added by simply including a non-stationary stochastic trend component in the factor dynamics. In this sense, FT is now the sum of two components, a stationary multivariate MAR that describes the explosive behavior of the process, and a non-stationary stochastic trend, MUT, that represents the pseudo-fundamental value around which the explosive behavior takes place. Now, an important remark here is that this is a framework that belongs to the observation-driven framework. So as you can see, both the bubble component and the trend component of FT are driven by the same source of errors. So it's always epsilon t, it's not a different innovation. And this is basically a location equivalent to the family of Garch models, where both the time-varying volatility and the process are driven by the same sequence of errors. Here is the same, but for the time-varying mean. Beta here represents a diagonal or matrix of coefficient that describes the strength of the update of this stochastic trend. Now, of course, this model is just an example in the sense that what I present here is very restrictive because it's assuming an explosive behavior for all unobserved common factors. And this is not realistic because while bubbles are an important feature of financial and economic data, they're actually not that frequent. So what is much more realistic is that a practitioner or a researcher estimating his own factor structure will find that just some of the unobserved components, either common or idiosyncratic, will experience explosive behavior. In this sense, the paper, more than a model per se, presents ingredients that can enrich a more general factor specification to include common or idiosyncratic explosive dynamics, and presents the assumptions, sufficient assumptions such that we can identify and estimate those explosive dynamics. So now that I presented the model, let me move a bit to the estimation. The estimation procedure relies on the two-stage procedure from Barigozzi 2021 for non-stationary factors, adapted to this type of setting. So in the first stage, we estimate the loadings and the factors using principal component analysis. Then the principal components are tested for explosive behavior, so we can identify which of these principal components, which of these unobserved factors have explosive behavior. And then in the final stage, we can estimate the dynamic properties of these factors. In particular, the paper provides sufficient conditions for consistency of the estimates of both factors, loadings, and parameters in the presence of such non-causal dynamics and heavy tail noise. And in particular, it's the heavy tail noise that makes this estimation different from the standard non-stationary factor estimation, because as we mentioned before, heavy tails are crucial assumptions for MAR model. And so we needed to loosen the general assumption of four bounded moment, that is what we get in the factor literature, to only a finite variance assumption. And we will see how this a more heavy tail setting will influence the estimation in a couple of slides. So now let me mention briefly what are the assumptions needed for the consistency result. The first assumption is that the first difference of the factor can be represented as a double-sided infinite MA sum. Importantly, this is a converging sum, and this means that when I mention non-stationarity, I'm ruling out I2 and higher order of integrations. For what concerns the errors that drive the factors, they should be IID random variables with mean zero and covariance matrix, the identity matrix. An important assumption is that the errors that correspond to explosive factors, so the one that have forward-looking dynamics, should belong to a distribution with regularly varying tail probability with index alpha greater than 2. This is a crucial assumption that concerns the rate of decay of the probability in the tail of the distribution of these errors. And this is the assumption that allows me to loosen the four bounded moment assumption up to only 2 finite moment while still maintaining the consistency result. For what concerns the loadings, we have that lambda prime lambda divided by n should go to the identity matrix, and the loadings should be uniformly bound. Finally, the first difference, the covariance matrix of the first difference of the factors should be a diagonal matrix with distinct elements on the diagonal. For what concerns the idiosyncratic elements, since we have a bit of a symmetric representation between what we can assume, the specification that we can assume for the factors and for the idiosyncratic components, we have the same assumption with the need to be representable as a double-sided infinite and may sum converging in their first difference. So now that we know what we need to, well, the assumptions that we need to estimate this thing, let's go to the consistency result. The loadings will be estimated by principal component on the first difference model, so that lambda hat, the loadings estimate, will be then defined by the matrix of standardized eigenvectors corresponding to the first R eigenvalues of the covariance matrix of the first difference data. Then, under the previous assumption, both the loadings estimate and the factor estimate will be consistent up to a sign change that here is represented by this S matrix for the true loadings and the true factor as an NT go to infinity. An important role in this picture is played by the parameter delta that drives the speed of the convergence rate depending on the time dimension. Delta is a parameter that depends on the tail index and so on how heavy-tailed are the process that we consider. Delta represents the price that we pay for a more heavy-tailed process. So while in general, in the factor literature, the convergence rate depends on t to the minus 1/2, we have that as close as we get to an infinite variance setting, the closer delta goes to 0, so the slower the convergence rate. While the closer we get to a 4-bounded moment setting, that would be the standard assumption, the closer we get to 1/2, that would be the standard convergence rate. So delta represents the price that we pay for allowing for a more heavy-tail setting. Once we can estimate these principal components and factors, we can then identify the number of relevant factors, and that can be done by using available procedures in the factor literature. A more important problem is how to identify which of these principal components actually have explosive behavior. And this can be done through a procedure that I propose in the paper that is an extension of an information criteria procedure proposed from Davis and co-authors, extended to a non-stationary setting. And in this way, we can identify which of the principal components have an explosive nature. Finally, once we've done all of this, we can get to the final stage estimation, where defining θ0, the true parameter vector, we have that under the previous assumption, the MLE θ hat will be consistent for the true parameter vector as an NT go to infinity. Now, this is clearly the crucial result of the paper, because identifying the true parameters that drive these unobserved components, I can reliably forecast the evolution of the process during a bubble, a common bubble, for example, and even test for the presence of a common bubble. That is exactly what we will do in the application in a couple of slides. Let me now briefly move to the simulations, where the simulation study I present a VGP were simulated for different combination of N and T to see how these estimates of loadings, factors, and parameters behave in finite samples. In particular, the DGP is a trivariate factor structure, where the first factor is a non-stationary explosive process, the second factor is a Gaussian random walk, and the third factor is an ARIMA 110. And this is exactly what I meant before when I said what is realistic is that there is a mix of different dynamics in our factor structure, some of which will be explosive and epithelial. In particular, F1T has errors that are t-distributed with 3 degrees of freedom. For what concerns the idiosyncratic components, we have that they are divided between a non-stationary explosive process, again, and a Gaussian random walk and Gaussian noise. So we have a system that can allow for both common and idiosyncratic explosive episodes in a mix of non-stationarity and stationarity. If we were wondering how this looks like, we have here the plot on the top that is simply the realization from such a DGP that shows some erratic behavior around some common dynamics, and in particular, the common explosive episode that we can see in the middle of the sample. And also, if we were wondering how a non-stationary explosive factor looks like, we can look at the bottom plot, where the orange line represents this simulated non-stationary explosive factor that looks like a non-stationary stochastic trap with some bubbles on top. Now, the blue line in the bottom plot is instead the estimate that I get of this specific and observed common factor through principal component on this specific realization of the DGP. Now, in the paper, I show how the estimates, both first stage and the last stage estimates, are consistent and go to the true value, then empty go to infinities, as one would expect given the theory. So in this presentation, I will try more to focus on the application that I think can be a bit more interesting. In the application, in particular, I analyze monthly price from stocks of 61 NASDAQ-listed companies in the energy sector, and the dataset consists of 353 observations that span from October 94 to February 2024. Here again, in the darker areas, I highlight the co-movements, and in particular, we can see this sharp increase and sharp collapse between 2008 and 2009 that is shared by most of the series in the sample. On this data, I estimate my principal component and try to find how many relevant factors there are, and 5 relevant factors are identified, and then I test this factor for explosive behavior, and one of them shows a relevant non-causal component, a relevant explosive component. And this is exactly what it's plotted in the plot below. So you can see in the background the raw data, while in blue you can see highlighted the principal component, so this is the fitted and observed factor, that is tested as having a significant explosive behavior. And as you can see, this is the responsible for the common explosive behavior that is observed between 2008 and 2009 and other small bubble episodes. The application now consists of a forecasting exercise to assess the ability of the model to predict the evolution of this explosive component, and a real-time test exercise to see if we are able to assess the presence or the emergence of a common bubble while it's happening. So, in particular, the forecasting accuracy is assessed during the growth and crash of the main bubbles of the sample, so 2007, 2009, and 2014, 2015, as highlighted in the plot below. And the forecasting performance is evaluated using density forecast. This is done to capture the bimodality of the predictive density of MAR models. This is an important feature. The predictive density of MAR models during a bubble splits in two, because it's always telling us that there's the probability that the bubble continues to grow and the probability that the bubble crashes. So to take this into account, I develop a performance measure based on the predictive density. In particular, I use interval forecast and construct a Di-Boer-Mariano test statistic based on this performance measure in the two samples. In particular, the non-stationary MAR model significantly outperforms the alternative model, that in this case is an epithelial ARIMA, in the two samples, showing that the non-causal dimension, so that this forward-looking dynamics really helps in forecasting during this common bubbles. And so this is crucial in terms of forecasting what happens in the system during a common explosive event. The final thing that we can do is that you can test for the presence of a bubble. We can ask at any moment ourselves the question, are we in a bubble right now? This can be done by decoupling, disentangling the fitted component, so the principal component that we fit, into its pseudo-fundamental value that I showed before, that mu-t hat, so fitted pseudo-fundamental value, and the mark component, and test if the deviation of the process from its fitted pseudo-fundamental value is explosive in nature. This is relying on a methodology proposed in a paper that I have with my supervisor. And this is done at any moment in time using only information up to now, testing if the last observation is significantly compatible with a bubble happening soon. And so this is done on an expanding window. And in the plot, I highlight the observation that at the moment in which that observation was the last observation, were signaled as significantly at risk of a bubble. As you can see, luckily, or for making me happy, let's say, the model highlights the bubbles of the sample as being at risk of a bubble, but importantly, the biggest bubble of the sample is signaled up to 8 months in advance with respect to the crash of the bubble, giving a significant advantage in terms of risk management, because you have to think that if there is a crash in this common unobserved component, it means that the crash is shared by all observation or all series in the sample to the loading matrix. So to conclude, the paper proposes a model that is able to generate common and idiosyncratic locally explosive patterns in a non-stationary environment. The procedure is shown to estimate consistently the common factors and their dynamics with good finite sample properties. And finally, the model proves to be a valid tool for real-time forecasting during these common explosive episodes. Thank you for your attention.